everyone. Welcome to this year's Caliper and Thicket tutorial. So today we're covering a few of the performance analysis tools for HPC programs that we are developing at Lawrence Livermore National Lab. So thanks for joining, everyone. And this, of course, is one of the tutorials in a larger series of tutorials that we have on the HPC software stack that we're developing here at Lawrence Livermore. So a few of the tutorials are still going on, and if you're interested in those, please just go to the link over there and check those out. So here's kind of the little agenda that we have for today. So I will first cover Caliper, our performance profiling library. It's taking about an hour or so. And then Stephanie Brink will cover Thicket, which is our performance analysis framework for analyzing large collections of runs. And well, logistically wise, we do have a live and kind of interactive hands-on session coming on later. And we have AWS tutorial instances set up that you can log into and that you can use for those. You can find the link here. This links you, or this gets you to a Google Doc where we have like more instructions on how to sign in there. And I think we also post that link in the chat and in the Slack channel. That's also a link from the WebEx chat here right now. Just a few little hints for that tutorial right now, if you already want to go ahead and take a little look. So it has a password, HPC tutorial 25. You can use any username that you like. So just save your first name followed by last name would be a good idea. There are a little login hiccups that we encountered. So usually you have to try in a couple times to actually get logged in. But yeah, we'll cover this again once we're getting to the interactive part of the tutorial. And yeah, if you have any questions, post them in the chat. And I think Stephanie and David Beckingsale can monitor the chat and ask if there's or interrupt me if there's anything that you would like, or if you have any questions that you want to let me answer. Okay. With that, let me start with the first part of our tutorial, which is Caliper, our performance profiling library. So as I mentioned, it's a performance profiling library, so it integrates performance analysis capabilities into the program itself. That's pretty useful because profiling is that way always available. You don't need any like third-party tools to mess around with, and that often simplifies performance profiling, especially for application end users who might not be familiar with those tools. So Caliper can also serve as a universal source code instrumentation interface. So it has kind of region annotations that you can put in the code to mark code sections that you are interested in. And it can use these instrumentation pointers itself and also forward them to other tools. So you can use Caliper as kind of a universal instrumentation library in that sense. And it's designed for HPC code, so it supports all the usual programming models, MPI, OpenMP, GPU programming models like CUDA and HIP, and also the performance portability layers that we develop here, like Raja, and Cocos, which is out of Sandia. What can you do with Caliper? So there's a variety of things. So you can use it for lightweight always-on profiling. So you can actually always have the program output some performance analysis information as it goes, like printing a brief runtime report for each run. You can use it for performance debugging if you want to drill down into some bottleneck that you suspect. You can even use it for introspection, so the application can itself query how much time it is spending in certain regions. We're not covering that in this tutorial, but it is an option. Now, one thing we use Caliper a lot for is performance comparison studies. That would be things like regression testing or scaling studies where you want to explore a large set of parameters that your program is running on, and then see how performance compares between different input sets, for example. And it's also very good for automated workflows because, well, it's easy to integrate or being a library in the program, it's easy to just automate performance data collection. So with that, Caliper is kind of a key component in the performance tools ecosystem that we use at the lab, and it works together with a bunch of other libraries and tools. And so here's a little overview of how it fits in. So as I mentioned, Caliper is integrated into our actual HPC applications and libraries through these instrumentation markers. And we often combine it with another companion library called ARIAC. And this library actually collects program meta information that tells you more about each run. So for example, what problem are you solving? What kind of input deck are you using? Who's running the program? What system is it running on? And that helps a lot if you want to do these large comparison studies later on. With that in place, Caliper can generate little reports on its own, but it is also the measurement components for our analysis frameworks, specifically Thicket, which is our programmatic analysis framework for comparing a large set of profiles across different runs. And also Treescape, that's another tool that we're developing here at the lab. And this is more specifically geared to the performance regression testing use case. So basically seeing how performance evolves over time as you're developing a program. Now, Treescape is currently in the process of being released publicly. So if you're working at Lawrence Livermore National Lab, you can ask us and we can tell you more about how to use it. If not, it's hopefully available pretty soon. And in the next year, we're running this tutorial series, we can include it there. In addition, you can also generate event traces and use them with tools like Chrome Trace browsers or Perfetto, if you're familiar with that. And as I mentioned, you can also forward Caliper annotations to other tools, in particular vendor tools like NVIDIA's Insight tools or AMD's ROCm tool stack. So yeah, as I mentioned, Caliper is a key piece in our performance analysis infrastructure here. So here's a bunch of tutorial material links. So specifically for Caliper. So the first thing is Caliper's own tutorial materials, which are part of the interactive instance that you find later on. You can also just download them on your own from the GitHub link that's shown up here. For Caliper itself, you find it in its on GitHub as well. So there's a link to the repo, so you can check out the source code, report any issues there. So we're usually using the GitHub issue tracker or the GitHub Q&A session for any sort of feedback about Caliper itself. And there's also links to more detailed documentation. Okay. With that, let me talk a little bit more about how we're actually using Caliper. So this is the general workflow that we follow. So as I mentioned, Caliper is a library, and we integrate it into our codes through the instrumentation interface. You're going ahead, marking different code sections that you're interested in with Caliper source code annotation API. That's usually the first step. And once you have done this, you can go ahead and use Caliper. To do that, Caliper is entirely configured at runtime. So to enable measurements, you give it a configuration in some way. And there are two ways to do this. Basically, we have an API, so you can actually control profiling programmatically through the program itself. Or you can also set environment variables, and that will tell Caliper what to do. If you don't do that, then Caliper is kind of inactive, and these annotation markers shouldn't really impact your code all that much. Oops, let's go back here. And depending on the configuration that you're using, you're getting different kinds of outputs. So these range from just human readable reports that you can print on screen or put in a file to machine readable formats that you can then process with various tools like Hatchet or Thicket that we're going into later, or trace browsers and things like that. So let's talk a little bit more about the instrumentation API. So as I mentioned, this is kind of like a key functionality of Caliper. That's actually what it started out as. And to mark regions in the code, Caliper provides a set of macros and functions for various languages. So we're supporting C, C++, Fortran, and also now Python. And typically what you do is you can mark regions with just a begin and end marker that tells it the name of the region. There are various different macros. So you have kind of the ability to specify granularity if you say have high level regions that you're interested in, or want to go more detailed and capture additional information. So in Python, there's also kind of like a high-level decorator interface that you can use to mark functions, but you can also use the regular begin end markers. These are also available in the Python API. And as I mentioned, on their own, these instrumentation calls don't really do much to actually make performance measurements. You have to select a configuration at runtime. And this means you can actually use or leave these annotations in the code, and they shouldn't really hurt your performance too much. Now, how do we usually go about instrumenting into code? So it's important to be selective. So it's not really meant to go down into like extreme levels of details, but rather meant to kind of follow the main logical subdivisions of your programs that you're interested in. Like, what are your kernels? What are your phases? And divide up your program that way. This is kind of an advantage of these manual annotations, actually, because, well, it avoids clutter that you get if you just instrument everything and lets you focus precisely on the things that you are interested in. Another advantage of the manual instrumentation is that it actually allows you to put like human readable names into the code. So a lot of the codes that we have at the lab are like heavily templated in C++. We're typically using frameworks like Raja for our codes, performance portability frameworks. And you can't really rely on compiler generated symbols if you want to make any sense of your program constructs. So it kind of allows us to put human readable labels in our code. And it's typically advisable to just like start small and add instrumentation incrementally. So just add a few regions and then add more detailed as you go. We now have explicit instrumentation support in Raja and Cocos for Caliper, actually. So the latest Raja release has this Raja name template argument where you can put in a human readable name, and you can use that as a Caliper region. And similar functionality exists with Cocos, so you can use Caliper as a Cocos profiling tool if you're familiar with that. They've had that functionality for a while.
Hey, David, before you move off of that, there's a question in the chat about would it make sense to have multiple sets of markers and then selectively sub-select some of those for different purposes? Or should you wrap them in defines?
Well, you can kind of do that. So, right. So as I have here on the left side, you have this Cali mark begin and the Cali mark phase begin. So these are kind of ways where you can define different granularities. So if you're only interested in like really high level regions, you can limit yourself to these phase markers. And if you want to integrate everything, you can then select at runtime that you want to have these low-level markers as well. So this is kind of like the only way right now to distinguish markers at runtime through the API directly. But if you really wanted to have like arbitrarily different sets of annotations, you would kind of have to find your own way of implementing that.
Great. Thank you.
Okay, so once you have your instrumentation annotations in place, you can actually do performance measurement. And the easiest way to do that is to use one of Caliper's built-in profiling recipes. So there's a bunch of them you can use. And one of them, for example, is the runtime report, which simply prints the time that you spent in your annotated regions on screen. You can enable those through the Cali config environment variable. So in an MPI program, the runtime report prints kind of statistics across your MPI ranks. So you see the minimum, maximum, and average amount of time that you spend in each of your annotated regions on the screen. So there's a whole bunch of different profiling recipes. I'm not going to go through all of these here. So we have the runtime report for regions. You have a similar thing for loops. You can have one for MPI functions. And then you have various ways of generating machine readable formats for Hatchet and Thicket and tracing as well. We also have this little Caliper program, which you can both use to actually look at files, machine readable files that Caliper generates, and also it serves as kind of like a reference documentation. So this -- help configs shows all the configs that are available. So these recipes are usually configurable, so you can add additional parameters to select additional features like more metrics, or change certain output options. So in the example here, we add the mem high watermark option, and that gives you the maximum amount of memory that you had allocated in each of your annotated regions. And you can also redirect output to files, for example, but here we're just directing it to standard out. So what are a couple of the things that you can do? So you can do MPI function profiling. So Caliper can automatically intercept MPI calls and show you the time spent in there. That's the profile MPI function. And when you enable that, excuse me, you see the time that you spent in, well, all your MPI calls. A similar thing is available for GPU profiling. So there are several levels here, so you can see the time that you spend in GPU API calls, both for CUDA and HIP. So the profile CUDA option here shows you the time that you spend in the CUDA API calls, like CUDA launch kernel, CUDA memcopy, device synchronize, and so on. And you can also actually see the time that you spend in GPU activities as a separate metric. That would be the ROCm GPU time and CUDA GPU time option. And Caliquery actually also helps you finding out what options there exist. So if you say -- help runtime report or other config name, then it'll tell you all the different available options that you have. So what are a couple of other things that we can do? So one option, you can do sampling with Caliper. So if you want to see more details that goes beyond the annotations that you have in your code, that's a really useful option. So with sampling, you see how much time you spend in actual functions, and you can go down to the source and line level if you want to, say, debug a performance bottleneck that you found in one of your regions. I mentioned you can also do event tracing and timeline visualization. So there's an event tracing configuration that will write Caliper files, and you can convert them into the Chrome tracing JSON format. So it's not super scalable because, well, this JSON file is kind of limited to just a few hundred megabyte to maybe like a gigabyte or so. And then Chrome will fail. But for small examples, it's really useful to see your timeline visualizations. And that, again, works with the Chrome Trace browser or Google's Profeto online tool.
Hey, David, quick question on the sample report. Can you use that with optimized code and no symbols, or do you need to compile with symbols?
You need to compile with symbols. You can use it on optimized code. So these things are really independent by now.
Thank you.
But yeah, if you don't have symbols, then you're not going to see much useful stuff, I would say. You still see what regions you are in, what Caliper regions, but not the function names or file line numbers underneath. Okay, what you also can do is, as I mentioned, forward annotations to third-party tools. So this is useful for many of the vendor tools that we have. So we have this for NVIDIA tools, the ROCm tools, and also Intel's vTune. So for NVIDIA, for example, there's the NVTX config that will forward all of Caliper's annotations into NVIDIA's own NVTX source code annotations, and then you can use it in the NVIDIA tools like Inside Compute, Inside Systems, and the ancient NVProf that we have here. But again, that also works for AMD and Intel. You can also collect profiles with Caliper, write it into a machine readable file, and usually you would look at these with tools like Hatchet and Thicket, but Caliquery can also analyze these files itself. So it has its own little SQL-lite query language actually, so you can go ahead and analyze traces or profiles with that. And in this case, for example, what we're doing, we're looking specifically at the time of MPI all reduce and how that behaves on all your MPI ranks. So you see how much time you spend on each MPI rank in this MPI all or reduce function in your annotated regions here. Okay, so one feature that's kind of unique to Caliper is the config manager API. So that lets you control profiling through the program itself. So your application can actually enable, configure, and start and stop profiling as needed. So to do that, you can create a config manager object and then add these recipe strings, the same ones that we use with the Kali config environment variable, and start and stop profiling with the start and stop or flush functions. And that way you can have a lot more control through the program itself on what you want to profile exactly. The API is actually also available in all the different languages that we support. So both C and C++ as well as Fortran and Python. Okay, so if none of the built-in recipes do what you want, you can actually configure Caliper manually as well. So internally, the functionality, the measurement functionality that Caliper uses is implemented in different little services, as we call them. And you can kind of combine and configure them individually as you like. And that allows really flexible kinds of performance analysis capabilities if needed. So in the example here, we are actually recording unified memory transfers in a CUDA system between host and device memory. And we're mapping this to named memory pools as well as the Caliper regions that they are happening in. So yeah, this lets you really build custom analysis solutions if needed. Okay, so how do we go about recording data for Thicket? So basically, Thicket is mostly used for comparison studies, for things like scaling analyses, input parameter studies, and so on. So you want to analyze like a bunch of different performance profiles. To do that, we have another config recipe called Spot. So Spot was one of the predecessors of Thicket. And that's what we're still using. So Spot will actually write a machine readable file in Caliper's own .cali format. And so you run all your experiments that you're interested in with this Spot config. You will get a bunch of these .cali files. You put them in an experiment directory, and that directory you can then load into Thicket and do your analysis. And Stephanie will, of course, tell you a lot more about that. So as I also mentioned earlier, Caliper works together with a little library called ADIAC, which records program metadata. And this is really important for these kind of comparison studies that we want to do with things like Thicket, because this tells you more details about what this particular one was about, what system is it running on, what is your input deck, and so on. So RDAC has two different kinds of functions. So there's kind of built-in functionalities for common sets of metadata, like as we see the username, launch date, MPI job size, and so on. And then it has this key value syntax for recording program-specific metadata. So here we're using it to, record certain input parameters that we're using in our program, and that gets combined with the Caliper performance data in the same file, so it's always available. And you can then use Thicket to slice through all your different experiments really easily. So there's a bunch of these built-in functions available. So I'm not going to go through all of these, but well, you can get your executable information about the system and so on. And there's a convenient shortcut now that we usually use, the collect all function, that will just give you everything that RDAC supports. The key value interface is available for C and C++, and we're working on a Python API as well. So that should be there soon. So in the C++ version, we have this RDAC value call, which accepts a bunch of different data types. So you always give it a name and then the data that you want to add. And well, it supports all the standard data types like integers, strings. It supports kind of special strings if you want to say something, for example, is specifically a file path or a program version number. You can mark these as these kind of special types. And it actually also supports compound types like vectors, lists, and so on. So you can actually go pretty crazy if you want to. However, I wouldn't overdo it because, well, at some point it gets more difficult to actually take these more complex types apart at the end when you want to do your analysis. So a similar interface exists in C, and there it's kind of using a printf style type descriptor. So you again put in your RDAC name, and then you have different type descriptors like %d if you want to put in an integer, or %f for floating points. And you have a similar set of different built-in as well as compound types that are supported. Okay, with that, let's kind of switch to the live demo part here.
So David, while you're doing that, I think we got through keeping pace with most of the questions. There's a couple lingering ones. There was a question, do you know which implementation of MPI run supports the -p flag?
Let's see here. Maybe there was a mistake on my end. And it should have been -n, but yeah.
N as in Nancy?
Yes.
For node? Okay. And then, let's see. Oh, okay. It says this was back a few slides, but your -p example might have been passing along the Caliper config values.
Yeah, that's right.
So which MPI run supports -p?
Let's see. I don't know where we had that, but that might just be the that's actually using the config manager API, right? So this is not going to MPI run, but to the application itself. And that will then set up the config manager with this particular configuration that you gave it.
Oh, okay. This was your MPI run -n, and then you had the executable, which had a -p flag, right?
Yes, I think so.
Okay. Yeah, so it's likely that the application implemented a -p flag, not MPI run, but the -p with the application allowed you to pass the Cali config parameters to the program.
So we can actually look at that with the examples that we have.
Mm-hmm. And then there was one other question about for your IO profiling. Do you have an integration with Darshan for that information, or from Caliper? How are you collecting IO information?
So we don't have an integration with Darshan. What we have in that area right now is you can intercept the POSIX IO interface. So basically just like the read, write, and family of calls. But that's
Have we talked
relatively
about
extent of it.
what are our thoughts about integrating with Darshan for this information? Have we looked into that?
We have not looked into that so far, but I'm happy to do that if there's interest.
Great. Let's see. Any other questions? There was another question about if your program or application wants to report, if you're just looking to report the time to solution, is it worth doing this via Caliper or just doing this with, your own clock calls in the program?
So Caliper is kind of meant to replace these own clock, or at least augment these own clock calls in the program. I mean, if you just have like one single thing, you only want the total time you spend in the program as a whole, then it might be overkill, yeah. If you do want to have more details and subdivide your programs and look at the different regions, then I think it would make sense to use Caliper for that.
Yes, that was my answer as well. I think, you could put in, I think what we found, right, is if each code was reporting its own time, there was a difference in if they were including in it and cleanup or excluding it from their total program time. And then we were also finding people were using different libraries for the timers, right? So we can't really do apples to apples comparison at that point. And so if you're built into Caliper and you're just looking for wall clock, you could start there. But then if you find that you spike at some point, you might, then look at the function execution times and be able to dig in on why your performance degraded for that run.
Yes, exactly.
And I guess you also get tools built on top of Caliper, right? Like in that workflow
Right.
that you showed at the beginning to do your post hoc analysis of the performance data.
Yeah, that's the other thing. So a lot of our codes actually had their own independent solutions for time measurements. I mean, they still have them, but they now augmented that with Caliper. And the benefit you have is that you get all the additional functionality that Caliper has, like measuring MPI functions or the GPU runtimes and things like that. And then the integration with this broader ecosystem like Thicket and yeah, all these other tools. Okay.
And then, sorry, one last question
Yep.
that's come in. Is Caliper used on our Livermore systems? And if so, why is it chosen? Why do we do it?
It's used on our Livermore codes, so I don't think they have like a referenced installation on the LC systems. And yeah, the codes use it because, well, it gives you access to the wider ecosystem of tools that we also have, like Thicket. So a lot of our codes do these performance regression testing analyses where they want to see how their performance develops over time as they develop the code. And we do have the tooling that makes that really easy. And well, it also supports all the yeah, all the systems that we are interested in the lab, right? So we have support for all of our GPU types, the large scale MPI jobs. And one more thing to mention, maybe as a library, Caliper is also kind of a robust solution for performance measurements. So a lot of our codes are really large, right? Millions of lines of code. And a lot of external or third-party tools can't really deal with that. But Caliper being integrated as a library is one way to add this performance measurement functionality in a pretty robust and well-supported way. So that I think would be another reason why teams use it. Does that answer the question?
I believe so, but please feel free to continue asking all these great questions.
So when you log into the AWS instance and you finally made it in there, this is what you find. So on the left here, we have the several parts of this tutorial. Well, today we're only covering Caliper and Thicket. We go into the Caliper part. You have, yeah, kind of the tutorial document. So this kind of yeah, you can use this later on if you want to go through the whole tutorial yourself. So you can load these things and make it prettier as well. And kind of follow along as we go here. So for the most part, we just need a terminal here. So let's just go ahead with that. So we have a couple of different demo apps here. They are also in this Caliper tutorial directory. And actually, it's a good idea to first look at those. So we have like a basic example. We have our Lulash proxy app and then XSBench. So the basic example is a really simple one that just demonstrates how one would use Caliper in the real code. And it's pretty compact. So just has these two little functions to demonstrate our annotation macros. So for here, we're using the C++ versions of it, where you only have to put this one marker into the code. If you're using the C version, you have to put like a begin and end marker there. And of course, try and mark all your function exits with it. And then in the main function, we have a few more of these markers. So we're marking the main function itself, and then a few different regions inside here. And we're also actually marking our main loop. So you can mark loops with, well, there are special macros for marking loops as well as loop iterations. So you can get iteration profiles out of this thing as well. And we also see that we use Ardiac here. So we're collecting all the default information that Ardiac has, and then some of the well, program configuration itself, like here the number of iterations that we're using. And in addition, we are also using the config manager, or well, we can optionally use the config manager, and in this case, we simply use the first program argument that we get into configure Caliper. So for codes that use CMake, it's pretty easy to add Caliper to the build system. So there is a Caliper package for both. Well, there is a package for both Caliper and Ardiac, so you can just use the find package calls and then add Caliper as well as Ardiac to your code with the link libraries call. So that's typically pretty easy. Okay. So the basic example should just be available in this tutorial environment. If we just run it, nothing happens because, well, as I mentioned, by default, the Caliper annotations don't really do anything. And we have to enable a configuration recipe to actually collect measurements. We can do that with the Cali config environment variable. Just use the runtime report. Try this again. And now we're getting our output. So since Caliper is configured as an MPI library, we're actually getting like the MPI version of this thing. So getting the time we spent in all annotated regions, the setup, the loop, and the foo and bar functions. Across MPI ranks, since there's only one rank here, they're all the same. And we can add additional functionality to the runtime report. So for example, we can use the print metadata option, and that will also print all the metadata that Caliper collects itself and through Ardiac. So if we do that, we get a bunch of additional information up here, like the library versions that we're using. And this is all the things that Ardiac collects by itself. So the username, user ID, launch dates, program executable. And then you remember we also added the number of iterations that we're using through this explicit Ardiac value call. And that's also being recorded here. And as I mentioned, we're also having the config manager available in the program. So, and we have it built so that the runtime argument is used inside the config manager. So if we do that, we also get our runtime report. Okay, so that's just a little basic example. Let's look at something slightly larger, namely Lulash. So Lulash is a little venerable proxy app from Lawrence Livermore National Lab. It's a little MPI OpenMP program. And let's first take a look at what we did there for enabling Caliper support here. So let's scroll down a little. So here we made Caliper actually a compile option. So we have our own set of macros called the lulash-mark function declared here, which just links to the corresponding Caliper call. If we want to enable Caliper, and then it's just empty if not. And then we are annotating some of our functions with it. So you see we have these markers in some of the functions, but not all of them. So as I mentioned, it's good to just basically mark high-level regions and not really everything, to keep both clutter and runtime overhead relatively low. So we're also collecting metadata with Lulash. So we added an additional function here that says record globals. So this again uses RDAC, and it collects all the runtime parameters for this particular Lulash run. So you can configure Lulash with a bunch of additional options, like the iteration counts that you have. You can give it a problem size and then some sync parameters. And we're recording this all with RDAC so that it's available for performance analysis later on. We're also recording some build metadata. So for that, we actually have a separate file that gets translated through CMake. And it, well, basically gives us the compiler that we're using and the compiler version and who built our code. So CMake will actually translate this into a C++ file that will get added to our code and then added into RDAC. And what we also do, and this is something that we relatively commonly do, is we add kind of global performance metrics, so the total time and a figure of merit for the total program run as RDAC values, and that will also usually help us quite a lot when we're doing comparison studies with Thicket later on. So you can quickly see how the overall performance is affected by certain program options or systems or scales, and then dive down deeper with the detailed performance data that you get from Caliper. Okay. So let's take a look at Lulash. So Lulash is called Lulash 2.0 actually, and it's an MPI program. And so we can run it with multiple processes. So here we actually have the Flux scheduler on the system. So we can say, well, Flux run -n8 Lulash, and we could do a small number of iterations and yeah, run and print out Lulash's own kind of report that it reports at the end. So, and again, since we didn't specify a Caliper configuration, we didn't get a detailed performance report here. So if we want to do that, we can either use the cali-config variable again, but as I mentioned, Lulash also has the config manager built in, and we can enable that through the -p flag, -P, and we can say we want the runtime report here, and that should then print one. Exactly. So now we see the time that we spend again in each of our annotated regions that we have in the program. And yeah, it's a little bigger than our basic example, of course. So what else can we do? Well, we can profile MPI functions, as I mentioned. So we can do that. And now we should see the time that we spend in each of our MPI calls in the code. So you don't explicitly have to annotate these, but Caliper can collect these automatically. And there's a bunch of additional information that we can collect. So for MPI, for example, we can record message sizes as well as MPI or as well as counts. So it will tell you how many and how many messages you sent and how large they were. give you statistics about that. We can record the metadata that we collected with ADIAC. And that's getting quite a lot, so we can actually write it to a file, report.txt. So we get our Lulish output, but we should also have this report.txt file. There it is. And yeah, now we see the metadata to be collected. So again, that's all the things that ADIAC collects by default. In MPI mode, it actually also gives you information about your MPI library and the number of ranks that you have. So here we're using mpage4 apparently. These are these Lulish specific configuration flags that we record through ADIAC. And these are now the build time flags. So we see that we built this with the GNU compiler 11.4. And we also have these global performance metrics that we collect with ADIAC here as well. So the total elapsed time and the figure of merit. And then for the Caliper part, we now have our whole report again with all this additional data that we requested, like the message counts and message sizes. So we see in which of all our MPI calls, or for each of our MPI calls, we see how many messages were sent there and how large the data volume was there. So you get statistics about that sort of thing. Okay. There are also more compact versions of the MPI report. So there's a configuration called the MPI report itself. And well, we can demonstrate that we can also do this through the caliconfig environment variable. So we do caliconfig MPI report. Then I should have given it a smaller number of iterations, or it will take forever. So okay, so yeah, now we get a more compact MPI report with just the MPI functions and yeah, how often you call those and how much time you spend in there. Okay. Any questions so far?
No, I don't think so. I think we're caught up. I was making sure everyone was able to get on the hands-on instance with you, but I haven't seen any issues besides the trying to log in multiple times.
Okay. All right. So now if you were to collect data for Spot or for Thicket, we can use the Spot config, as I mentioned. So just as an example, we can collect configurations again, and the Spot config is the one that will record as data for analysis with Thicket and Treescape also. So if you do that, what? Oh. You should now get a Caliper file with an auto-generated name. So you can also give it a custom name if you like. But if you don't, then Caliper will generate a unique file name. And we can actually look at this with the Caliquery program. -t is a good option if you just want to see what is in one of these .cali files that will generate a report that's quite similar to the runtime report. So we can give it this file. And it's probably going to be a little big, so we can pipe it into this less program. And yeah, this will give us a report that's very similar to the runtime report. The kind of information that the Spot config collects is very similar to the runtime report. So it also basically gives you the time you spent in each of your annotated regions. It actually collects both inclusive and exclusive times. And also the number of function calls. And same as with the runtime report, you can add additional options to the Spot config to get more metrics. So you can, for example, also collect the MPI message statistics in the spot config as well, and a whole bunch of other metrics. So yeah, if you have a bunch of these .caliper files, you can put them in a directory and then yeah, point them to Thicket and analyze them there. As I also mentioned, Caliquery kind of has a help function. So if you do like a help runtime report, excuse me, it will give you all the options that are available. Yeah, for the runtime report, we have a bunch of things like the MPI statistics that I mentioned. What else? You can do the region counts as well. So if you run your region counts in your runtime report, you can do that. You can do region stats. That's basically region instance stats. That's probably kind of interesting. Let's briefly do that. So runtime report, the region stats. And let's also put this into a report, into a file. So this will give you per visit statistics. So if you have, well, some of these functions you're iterating over quite a lot. So this calc energy for elements was called 1100 times. And the shortest one of these took like well, that's 2 microseconds basically. And the longest took 148 microseconds. So you can get more detailed statistics about your function calls like that. Okay. Do I have a few more minutes, or do you want to move over to the Thicket part?
No, we've got time, so I think you can continue to show some of the features of Caliper.
Okay.
Let's see. I guess we'll call this your free. People can suggest things that they would like to see and test your live demo. There's a question about ignoring certain iterations in the region count. So ignoring like the first iteration.
That's a good question. So, I mean, you can make it work through some custom configs, probably, but it'll be a little more involved. I mean, if you only want to ignore it from the output, that's a little bit easier. But first of all, we need the iterations in there. Well, and let's actually do that. So let's collect the trace with Lulesh. Page, finish. Let's give us 10 iterations and do an event trace. Oh well. This will actually give us a whole bunch of Cali files, and one for each process, and we can actually give them a name by rank. So that's another cool thing you can do. Yeah. Need our -p. Okay. So now we should, what? Oh. Okay, that's a little bit tricky. Let's do that. Okay. So we actually have to enable a MPI interception to get this MPI rank variable. But now we have a bunch of trace files, each of them, well, having each begin end event. From this whole program. So it's generating quite a lot of data. Namely all this. But we have a bunch of things in here. So if we now want to do the whole exclude the first iteration, we can kind of write a query that does that. So we want, let's say, you can write your own custom query. And first do it like that. So this should, for our trace files, this should turn them into something like the runtime report again. Oops, and it does. And now, well, let's take a look at this thing. So we see that we call what's called once in each iteration, like the calc time constraints for elements, for example. Now we can actually filter this by the iteration. I think I called my loop bullish cycle. And now we can have maybe then 2. And now, yeah, we only have 7 calls for this. Oh yeah, okay, yeah, that's correct. Because it's now going from 3 onward. So that's a way to exclude your first iterations, at least from the output. So you can write configurations that do it. It's all possible. But yeah, sometimes it can get a little involved. Is this something that would generally be useful? I can, of course, also try and add this as an option in Caliper. So just let me know if that's something of interest. So in short, it can be done, but it's, yeah, tricky.
Okay, nicely done, David. I know we're testing all of your live coding. There's another question about if you have a Python example in this tutorial. I know we recently added Python bindings, but I can't recall if you had a chance to add in a Python example to this.
Yeah, we don't have one in the tutorial, but it's a really good question, and I think we should add one for the next tutorial at least. So there are some examples in the Caliper documentation, which is, oh, so that's the main Caliper documentation page, and there is a chapter on here on the Python support. So, and that has a larger Python annotation or instrumentation example as well. So I'm hoping that helps. But yeah, we should definitely add an example to the tutorial as well next time. And these materials should all be linked from the slides and from the tutorial materials that we provide. Okay. Yeah, one more thing I can at least show is a little bit of what we can do with GPU apps. So, well, I don't think this is a GPU-enabled AWS instance, so we don't have that here. But I can a little bit of what you can get. So the profiling CUDA.md is kind of the GPU part of the tutorial. So we have a separate example called Access Bench. That's a CUDA application. And there too, we have a bunch of Caliper instrumentations in there around all the different GPU kernels that the program has. If, again, you just do basic runtime profiling, you get the time that you spend in these annotated regions. So that's fairly straightforward, but you can enable the profile CUDA flag or profile HIP if you're using an AMD GPU. And then you get the time you spend in the CUDA API calls, like all the stream synchronizers, launch kernels, and so on. And you can also profile the GPU activities themselves. So that would be all the memory copies and kernel executions that happen on the device. So you see both the time that you spend in your host code, as well as the time that your activities are occupying on the actual GPU. So remember, we had this code annotated, and well, it will tell us that for the different GPU annotated regions, we spend in this case 0.1 seconds on the CPU, and well, almost as much on the GPU. So this particular region was utilizing the GPU quite effectively. So you get like 99% GPU occupancy in there. You can also view memory copies. So you can see how much data you are transferring from the CPU to the GPU and vice versa. And the access bench example basically moves data only from the host to the device, but not back. So that's what we see here. And we can also view at individual kernels. So there's a show kernels option, and that will show you the individual GPU kernels that we're executing. And we see we have both the program's own kernels that it implements, and then also all the library functions that it calls from the CUDA thrust library. So there's a lot of additional things that you can see in GPU codes as well. Okay. With that, I think I'm pretty much at the end of the Caliper part. Are there any more questions?
In the first session, David talked about how we collect performance metrics using Caliper. And in this section of the tutorial, I'm going to be going over our essentially mentioning Thicket and Hatchet, which are two of our post-processing tools that we develop here at Lawrence Livermore for analyzing performance data, such as that coming out of Thicket. Or sorry, such as that coming out of Caliper. So just some basic logistical information to get started. These slides are uploaded to this link here, and maybe I can copy paste really quickly so people have it. If you'd like to take a look on your own as we're going through this presentation. And let's see, and then similar to David, we'll go over some introductory slides for Thicket with this presentation, and then do a hands-on session at the end using the AWS instance. So feel free to stay on the AWS instance, especially if you went through some of the pain points of trying to log in several times. We'll use the same one. Okay, so the challenge we're trying to solve is doing performance analysis in a increasingly complex HPC ecosystem. So our software and our hardware, as we know, are becoming more complex. And so in this environment, we're trying to understand some things like how our applications are strong scaling or weak scaling. We want to understand what the impact of different application parameters have on our performance. We'd like to understand how the choice of which compiler we're using and what optimization levels impact our performance, what the performance across different hardware architectures looks like, in particular, the performance of CPU versus GPU. And then we want to be collecting different performance measurements from these different tools. And so how do we collate them into one kind of performance landscape? And so our goal here is really to be able to analyze and visualize performance data from all these different sources and different types. So here is our big picture solution for analyzing and visualizing performance data from the different sources and different types. So here in step one, we're running our applications or our codes with different measurement tools, right? So David went through Caliper in the earlier module. We also have tools like NVIDIA Insight. AMD is standing up lots of tools that are similar. We have Tau, HPC Toolkit are some of other examples that we use for measurement collection. And so from this running our applications with the measurement tools, we generate call tree profiles here in step two. And you can imagine that as you're doing multiple studies running across different rank counts or changing parameters or changing compilers, you can build up this kind of directory structure of different profiles that you then want to analyze. So in step three, we load all of that performance data into a Thicket object, which we'll talk more about in the next few slides. And then once you have your data loaded into Thicket, which is built in Python, you then can enable this exploratory data analysis, which is really, you can kind of take advantage of all of the libraries that you have available to you in Python to do things like clustering, be able to analyze and model, generate figures, and do data manipulation as well. And so Thicket is developed at Livermore. We are up on GitHub, and so here's links to our source code, as well as the Thicket tutorial, which is available in your AWS instance. So a little bit just about what our profiling tools collect, and David again went over this in his Caliper module, but the idea is that we collect 3 different things with our profiling tools. The first being a call tree shown on the left, right? And a call tree is simply a graph showing you which functions call other functions in your program. So in this example, we have a function main that calls foo and bar calls another function baz. Also in our profiling tools, we collect performance data, of course. So for every function in our call tree, we might get performance data such as how much time the function took to execute. Maybe we're interested in how many cache misses or how many memory accesses happened per function. And the third thing that we expect our profiling tools to be collected is this metadata per run. So with Caliper, we're using this through Audioc, which is another library developed at Livermore. And this is giving us information such as, who ran the job, where did they run it, what time did they run it, how long did they take to run the job. But it's really just any information about the single profile that you collected so that you don't need to embed a lot of that information into your directory structure names. It's easy enough to reference from the file itself. So Thicket builds upon another tool that Livermore developed, which is known as Hatchet. They are, very closely related, but Thicket has built upon what Hatchet started. So in Hatchet, we had this notion of a graph frame, and a graph frame consists of a graph shown on the left as well as a data frame. And so again, a graph here is a call tree. It's storing our relationships between the parent functions and the children functions, so indicating which functions called other functions. And then we also have a data frame component that exists alongside the graph. And so for every node in the graph, we have a row in the table, and we store various metrics that go along with that function in the graph. And so this could also then be unique per rank or per thread, depending on how it is that you configured your data collection. And so Hatchet is also online at the links down here on the bottom. Really so Hatchet was where we started. We were interested in doing programmatic analysis on particularly Caliper files because that's what a lot of our code teams are using. And so we were interested in looking at maybe 1 or 2 Caliper profiles at a time. But then we, of course, wanted to be able to look at lots and lots of different Caliper profiles at once, which is not what Hatchet was meant to do. And so that's what Thicket has really subsumed in that area. So looking a little bit more into Hatchet's constructs, because these are, again, what Thicket uses because it's built on top of it. So if we want to look at or visualize Hatchet's graph frame components, that being the graph and the data frame, we have print API functions in Hatchet. So for printing of the graph, we do a print GF is your graph frame and .tree. And so you get this terminal-based output here. It is by default a red-green color, and so red is going to be colored for the higher end of the metric that you're printing alongside the different nodes in your tree, and green will be on the low end. And so the idea is that when you print the tree and you see what things are red, that kind of draws your attention to this is where the hotspots are in your call tree. And then the data frame, because it's a native pandas, we can simply do a print on the data frame itself and get a table representation in our output to see what the data frame looks like. So we can compare graph frames we can compare 2 different profiles in Hatchet. In this example, we're looking at dividing the 2 graph frames to compute our speed up. And so you can think of, while we're showing division, you can also do this to add or subtract or multiply. And so when we're wanting to do this in Hatchet, the first thing that we're going to do is determine if the trees of the graph frames are the same. And if they are not, we're going to unify them so that the structure is the same. So for this example, we're showing just a very small tree, right? We're trying to unify a tree with 3 nodes, foo, bar, calls corge, and unify that with a very similar tree, foo calls bar, but is also calling baz and growls. And so when we take the union of this tree, we're simply going to be adding another call from bar to corge to capture the all of the connections between the two graphs. And so in our example down here on the bottom, we're doing a GF1 divide by our GF2. So you can think of this as, a CPU versus a GPU run, or maybe a 1 rank versus an 8 rank run, and you're wanting to compute the speed up. So under the hood, we're taking the union as we showed at the top. And so for nodes that exist in both of the trees, we're going to take a simple division or simple operator of the metrics in the tree. So 6, sorry, the way to read this is the middle one over the right graph, and the result here is on the left. So 6 over 3 gives us a result 2 associated with bar. And then for nodes that don't exist in one of the 2 trees, so for example, Garpley and Grout down here only exist in GF2, we're going to include those because they're part of our union tree. But our math in Python, when you divide nothing by a value, you get nan. And then the unique thing that you'll get in your terminal-based output are these red and green arrows to indicate which graph that it originated from. So in this case, our result has this green arrow pointing to the right. And because we're looking at this formula here, the right arrow is indicating the right graph frame, so GF2. Okay, so when we think about this in the Thicket construct, we're using Thicket to compose multiple performance profiles in Thicket. So if we have 2 profiles, P1 on the top and P2 on the bottom, each profile has its own metadata, its own graph, and its own performance metrics. So we're going to do the same thing like we did in the previous example. We're going to take a union of all of these different elements. So the first thing that we're going to union or compose is the performance metrics table. So each of the functions in our graph now has 2 rows, 1 row for each profile. So we bring down the 24 cache misses from profile 1, and we bring in the cache misses of 16 from profile 2. The next thing that we're composing is the metadata. And so every row in our metadata table in Thicket will just be a count of how many profiles that you've read in. And then the last component that we have in a Thicket is called this aggregate statistics table, which allows you to do order reductions over the performance metrics table. So the performance metrics table is going to have data from every profile that you run, but you might be interested in taking, what is the average cache miss count across all of my profiles. And so that's why we have this aggregate statistics table, so that you can keep record of that sort of information if you're only interested in kind of an overview look across all the profiles. So the Thicket profiles, or the Thicket components, are interconnected. And so what this means is if you're impacting or filtering or removing rows from the metadata table or the performance table, the associated elements within the Thicket object will also be updated. So in this case, we have 2 profiles, and our filter here is we only want to look at profiles that came from a particular platform, which is called Lassen, and I only want the profile that was run by Bob. And so on the right side, once we filter our Thicket, we will only have 1 element or 1 row in our metadata, and then our performance metrics will also be filtered such that we only have data from profile 2. So the way that we imagine people using Thicket is you basically you can generate Caliper files from many different runs. You read in all of the profiles into Thicket, and then you leverage the Thicket APIs to be able to filter and focus your analysis into particular profiles of interest, instead of needing to filter which profiles you want to read into Thicket, like from your file system itself. And so our big thing with Thicket is really embedding as much metadata information into your performance profiles because it is so powerful and useful for being able to manipulate your Thicket as a post hoc process. Right, because all of the metadata is now embedded into the Caliper files itself. And so you no longer need to make sure that you put in all of this metadata information into the various directory structures, right? I think we've all done the top directory structure name is the number of ranks, maybe it's the date, the machine, which compiler optimizations, what parameters you ran with, right? I think we've um, written many scripts where we append all of that information into our folders and then we store the Caliper files underneath. We're really hoping to embed all that information into the Caliper profiles themselves so that you don't need to be keeping track of it on the folder names. Okay, so we talked about how Thicket, we load the data into Thicket. It has these three different components. It's got your graph. We have a performance data table, a metadata table, and then we've got your aggregate statistics overall over the performance data. We're interested in being able to compose data from different sources and types, and this Thicket object allows us to do that. So we can look at different scaling, different application parameters, different tools and hardware types. And so the next set of this talk will go over some of the example exploratory data analysis that we've done on our thickets. And so we can look at how we visualize, how we manipulate the set of data, how we cluster. So let me pause here. Are there any questions I should answer before I move into the case studies?
Not yet. Oh, yes. Do you have a recommendation for storing cluster architecture in Thicket?
Cluster architecture, that's hardware cluster architecture.
Yes.
So if that's so Audiac allows you to write in any kind of custom metadata that you like. So if there is a C or C++ or a Python API that can get you the that information, we can record it in Audiac. I think David, you already are recording the hardware type as part of the your collect all Audiac function.
And
I feel like I've seen Power
not
9
yet.
or
Not yet.
x86 as one of those.
Okay. Yeah, maybe. Have to double check, but certainly something that can be added at least like at the 86 or x86 level. But it's getting a little more complicated if you like want to know your specific GPU hardware and things like that.
Yes. Yeah, so there we have, as David had mentioned, in Audiac, there's a function called collect all that can give you some base set of metadata, but you're free to add any type of other metadata. You just need to add, there's an API to customize which metadata you want to add. And so the hardware could be one of those. Okay, I will continue forward. So we're going to look at some case studies that we used first with some Thicket analyses in the next few slides. So the first one is the Raja Performance Suite, and this is an open source suite of loop-based kernels that we commonly find in HPC applications. And so this is really a way for us to showcase the performance of different programming models across different hardware. And there's a GitHub link here on the right. So in our data set, we are looking at 560 runs or Caliper profiles. We looked across two different clusters. One is a CPU only, and one was a CPU plus GPU system. We looked at four different problem sizes for the Raja Performance Suite, three different compilers, four different levels of optimizations. We looked across three different programming models and three different performance tools to get to our 560 profiles. This screenshot here on the bottom is showing our what our metadata table looks like in Thicket. So we have our two clusters, Quartz is our CPU only, and Lassen was our CPU plus GPU system. Oh, David, this might be where I'm recalling seeing x86. So there's a systype build that gets collected as part of the collect all API in Audioc, and so this might get you a little bit of a sense of what the underlying hardware is. This is, of course, on an LC system, so it'll show up a little bit differently depending on which system you're on. But you can see in Thicket, we take a list of the different problem sizes, the list of different compiler optimizations. So it's a really nice way if we can read in all of our profiles into Thicket. Printing out the metadata table gives you a nice look at all of the different parameters that you iterated over for your runs. So we used Thicket to compose across profiles across different platforms, profiles across different tools. So in we had two different thickets. Our thicket object in the top is composed of two profiles that were run on the CPU. So this is a snapshot of them, of course. It's a much bigger table, but we're looking at two different problem sizes for two different nodes in our tree. And we were collecting I guess these are the top-down analysis counters for our CPU-only run, so retiring and backend. And then our bottom thicket here in the middle was collected by running two runs on the GPU, and we were using Insight Compute to be able to collect some GPU metrics. And so we basically want to compose these two different thickets so we get a single thicket object that has our CPU data plus our GPU data. So when we compose this, we're taking data from our CPU thicket up here and placing it into our bottom result table here. And then we simply are expanding or extending the information by bringing in or composing in our GPU data as well. And so what you can see in our results now is that we have, for each node in our graph, we have all of the CPU data and all of the GPU metrics in one table. And this makes it much easier for us to do analysis and plotting because we're referencing it from the same, a single thicket object. So building upon that, we have a slightly larger data set here that we generated to look at CPU and GPU performance and also to look across multiple tools. So in the example before, I was just looking at two of these items in the list here, but for this thicket that we're composing, we're bringing in four different information from four different sources and types. So we have our basic CPU metrics from Caliper. So that's item 1 here in the bottom of our result table. So that's getting us the exclusive time for each of our nodes. And then bytes and flops per rep are coming from our application, the Raja Performance Suite itself. Our second set of data are using the Caliper PAPI service so we can collect top-down metrics. So like instruction retired and backend bound. Our third set of metrics is the GPU runtime, which we collect from Caliper. And then our fourth set of metrics are the GPU metrics that are coming from Insight Compute, right? And so this really, we had to do this in 4 different runs because, of course, you've got overheads that get introduced by adding the PAPI service or by adding additional tools into your collection. And so we really tried to isolate the data collection by running this as 4 different individual runs. Oops. And so some examples of analysis that you can do once you have all this information in the Thicket object is compute your CPU to GPU speedup. We could also then be able to correlate our memory and compute usage on the CPU and the GPU by having all of this information in a single performance landscape. So one of the things that we were able to do here is we had information from these 1, 2, 3, and 4. And once we had that into a single performance landscape, we were able to add in this column that we called speedup, which is a derived column that we did once we had all the data in the Thicket object. And we can see that this node called apps vol 3D, which is the first row, had a higher speedup than the LCal's Hydro 1D. And we can start to look at have that information alongside our, let's say the GPU metrics to indicate why is it that the speed up was higher for AppsVol 3D versus LCal's Hydro 1D. And perhaps it has something to do with this DRAM throughput, for example. Okay, so the next thing that we're going to look at is how we
Stephanie.
Yep, go ahead.
Like one question, so do you support serializing Thicket objects for analyzing in non-Python languages?
Do we serialize for analyzing outside of Python?
Yes, I believe.
Oh, we have not had a use case to need to do that yet. We do support some, obviously, the more data that you're trying to read into Thicket, the slowdown of Python can occur, right? So we try to support as much as we can so that, you only have to read in a big amount of data once, and then you can export into, we can pickle it so that after you do your analysis, you only have to read in a subset of it. But we haven't found a need yet to be able to support analysis in a language outside of Python. But we'd be happy to hear it and think about supporting that down the line. Okay, so the next example I want to show is how we filter using a call path query language that's been built into both Hatchet and is being used by Thicket. So on the left, we have a input call tree, and this is a call tree that's shown from the Raja Performance Suite. And with our filtering on the call path, this allows us to leverage the call path when we're doing the query language. So we can really start to extract particular, I guess, layers out of the call tree, like, for example, the MPI library call tree. So in this example, we want to filter on a call path, and we want our subtree to start with a node name based, a node called base CUDA. So we're going to put that here on the right, which is our output call tree. And then we're interested in nodes that end or contain block 128 and also maintain any of the nodes in between that, right? And so from the left to the right, we're only keeping our block underscore 128 nodes, as well as the parent that falls with that. So we get our base CUDA as the root. We're only looking at algorithm, and then we're keeping the children that have this block 128 node in them. There's certainly lots more powerful queries that can be written with the query language. Our student Ian Lumsden, who's online here, has a paper at eScience that kind of walks through the details of the query language if you're interested in writing some more detailed or complex queries. But this gets back to the question from the Caliper section this morning, which was asking about writing, having, I guess, different levels of Caliper annotations. If you're more interested at a higher level or more interested in Caliper calls at a lower level in your application, you could still be having all of those Caliper annotations on and collecting profiles with all of those annotations, and then using Thicket to do the post-processing with the filter. So you only look at particular, today I'm only interested in these children with block 128, but tomorrow I might be interested in the entire call tree. Okay, so we also did a top-down analysis, which is based on Intel systems. There's a paper reference down on the bottom right if you're interested. But the top-down analysis uses hardware performance counters in a hierarchy to identify bottlenecks in your CPU pipeline. So at the top, the ones that we were interested in for our experiment was these top four here. So retiring, bad speculation, front-end bound, and back-end bound. But you can see in this hierarchy that, if you collecting memory bound or ext memory bound or mem latency, all those kind of filter underneath the larger back-end bound. So by collecting metrics that fall underneath each of these top four, you can really start to get a sense of where your pipeline is stalling. So Caliper has a top-down module that exists to derive the top-down metrics for the different call tree regions. And so that's what we used to collect our data set for this analysis. In Thicket, we have developed a tree plus table visualization, and a screenshot is shown here on the top. And this can show the top-down metrics as stacked bar charts. And so each bar in this figure is a different profile. So there's 10 different profiles that we collected for each of problem size in the Raja Performance Suite. So 1 million up to 8 million. And then we get each of those for the different nodes in the tree. And so we can visually see, looking at AppsVol 3D, this has the highest retiring rate. So it's the most, looking at the blue. So is the most blue as we look across the different problem sizes. And if we look at LCal's Hydro and Stream Dot, these tend to become more back-end bound or more red as the problem size grows. So it's a nice, quick, easy way for you to be able to visualize some of the top-down metrics for each of the nodes in your tree. So because Thicket is built in Python, you can easily leverage third-party libraries such as scikit-learn to do clustering and ML algorithms. So the example here that we used is k-means clustering with scikit-learn on our Raja Performance Suite data. So for this data set, we filtered to look at only the largest problem size we ran, which is 8 million. And then we use that call path query language to extract all implementations of our stream kernel. We normalized and then we applied the scikit-learn clustering to our top-down metrics of runs, looking at different compiler optimizations and different levels to generate these figures. And so we can see that our clustering identified 4 different clusters marked by a 0 or a circle, an X, and a square. And we're plotting just 2 of the top-down metrics of the 4 that I was showing you earlier. These showed to be more interesting as compared to the other 2, the front-end bound and the bad speculations are the ones that we are not showing here for brevity. So we can see here our group 0, or our cluster 0 here is mostly our add, copy, and triad. And it includes all different optimization levels, right? We've got green and blue and orange and yellow for our different optimization levels. Our group 1 cluster includes all of the optimization level 0. And then our group 2 or our cluster 2 includes our stream dot and our stream multiply and mostly focuses on optimization O2. And I guess the other interesting thing that this did highlight is that O2 proved to be our best performance. We had the highest speed up with our O2 optimization levels and was something that we were surprised by and something we wanted to dig into. All right, so our next case study is looking at Marble, which is a next generation multi-physics code developed here at Livermore. For this study, we had 60 different runs or Caliper profiles. This spanned across 2 different clusters, a system called RZ Topaz, which is a LC machine, and then we had a cloud-based system on AWS. We looked at 2 different MPI libraries, 6 different rank counts, and then we repeated each run 5 different times to look at noise and variance. So the first thing we had to do was compute the noise and the scaling for our data. So we used, if this is our input Thicket object in the data frame, you can see that for a function main, we have several different world sizes, and we do repeat runs. So you'll see there's, you see 3 instances of 2000 ranks. You've got 2 instances of 144 ranks, for example. And so we use the group by on the world MPI world size to generate unique subsets of the data, which is the repeat runs, and then we can compute noise on that. So after we run this group by, the result here is on the right. So you get 5 different rows in the performance table relative to the particular world size that you ran with, and then you can compute an average or min or max to indicate what the noise is. And then we compose the runs across different platforms and at different scales. And once we do that, we have all the data into our single Thicket object. We can generate a strong scaling plot using matplotlib and get a figure like this on the right. And so we've got the ideal lines drawn in the dashed for Intel MPI and OpenMPI. And then we've got our results here shown in the blue and the gray solid lines. And then the shaded region is the deviation, and the dots are the average that we computed across the 5 different runs. I think we, in our figure, forgot to draw the variance for our blue line, but there is some variance there. And so what this figure was showing us is that Intel MPI and OpenMPI scale well up to 16 nodes before they start to diverge in the performance. So one of the other things we can do with Thicket is take advantage of another third-party library, Python library called XtraP. XtraP derives analytical performance models from an ensemble of profiles that cover one or multiple modeling parameters. And so for our use case here, we selected a function of interest out of the Marble code. And so this was this msolver molt function. And then we called XtraP to model the scaling on different hardware types. So we have our AWS system here on the left and our CTS system here on the right. The red dots is the data that we collected, and the blue line is the model that was drawn by XtraP based on our data. And so we basically are able to derive models about how the performance might be at higher process counts. So we can see that AWS is slightly better in terms of performance at higher process counts than our CTS model. So we can also visualize metadata once we have it, looking at parallel coordinate plots. So Thicket has this figure is a screenshot, but Thicket's developed an interactive parallel coordinate plot so that you can show the relationship between the metadata variables and look at metadata versus performance data. So it's really this is another kind of tool in the Thicket toolbox of how to visualize and analyze the data. There are many ways to do this kind of analysis and look at the relationships if you're not so keen on an interactive plot, but we provide a lot of different ways for users to be able to look at the data. But the interface will be similar to this. The lines and the dots will not be colored upon reaching this page. But in the upper left, you've got a metric value that's associated with a single node in the call tree. So you can look at, there's drop downs here, so you can kind of pick and choose what it is that you want to look at. So for this one, we're looking at a metadata value of the maximum number of elements versus the inclusive time duration. And on the right, we're looking at the rank count versus also the performance over time. And so the bottom here is our parallel coordinate plot. So usually people see them kind of upright, but we draw it in a horizontal fashion just for to take advantage of the space. And then you can kind of click on different lines to indicate, or I guess you click on these crayons to indicate how it is that you want to color the lines and the dots in this visualization. So in this example, or in this screenshot, we are coloring by the architecture. So RZ Topaz is the point here on the left side of the architecture line, and the AWS system is here on the right. And so we can essentially easily be able to trace these lines and say that the orange lines, if I look at wall clock, are always performing worse than the AWS system. And so we might look into why it is the case that that RZ Topaz is performing worse. So the other thing that we've developed in Thicket is a way to look at performance fluctuations over time. So with Caliper, you can collect performance profiles at different intervals while your application is running. And so you might be able to, at iteration 0, be able to check how many iterations have you run, how much progress have you made. And then we can with Thicket, we can categorize temporal patterns that we leverage from this paper reference down here on the bottom left. So the categories that we are developing in Thicket is a constant, a phased, a dynamic, or sporadic. So you can read in all the Thicket profiles that you've generated over the course of your iteration-based collection. and then be able to say, like, was there a constant pattern when I'm looking at this particular metric? Was it dynamic as I look across these different profiles? And so we've developed more terminal-based representation in the symbols that we would add to the Thicket call tree visualization if you're interested in looking at this kind of information. So like I said, we display the pattern symbol and the temporal score as part of the call tree now. So you can kind of see after the metric itself, we print in whatever kind of arrow that mimics the category that we're seeing for this particular node in the call tree. And then we can use Python plotting to create a more granular visualization, right? So we can now be plotting over all the iterations that we collected, the different execution times, seeing how those vary over time. Okay, so to wrap up the Thicket piece here before we dive into the hands-on, Thicket's a toolkit for exploratory data analysis of multi-run, multi-ensemble data. We showed with Caliper how we run our code and collect call tree profiles with Caliper. We can also do this for other tools like Insight. We can load the data into the Thicket object, which consists of these 4 different components. We've got the call tree or the graph, a performance data of metrics, the metadata about each of the runs, and then the aggregated statistics table. And once you have your data loaded into Thicket, you can then take advantage of the many different Python libraries to do exploratory data analysis, like clustering, modeling, generating plots and visualizations. And here's links to our GitHubs if you're interested in our source code or in any of our hands-on piece. Okay, so with that, I'll show this screen in case we've got new folks that are hopping in and would like to be on the hands-on tutorial piece. But David, are there any other questions that have come in? Let's see. Okay, so I'm on the instance, and at the root we have David looked at the Caliper-tutorial directory, but we'll dive into the Thicket-tutorial. And here you've got the data that we use for the tutorial, but we'll click on notebooks. We include 2 notebooks in this repo or in this AWS instance. The only one we're going to go over together is number 1. So I'll open that one. But the other one that we include is a tutorial to generate some of the figures from the Raja Performance Suite case study that we were looking at. So looking at how we did the k-means, clustering, for example, those are reproduced in this notebook if you're interested, and the data is also there as well for you to play with. Okay, so I'm going to, just for the sake of things, I'm going to hit restart kernel and run all the cells and let those go. Okay, so we're loading in our different packages. You'll see that Hatchet, like we said, is something that Thicket is built upon. So we still use it as a dependency because we're using some of their interfaces. So we include Hatchet or import Hatchet. We also import Thicket. So for our first set of examples, we're going to read into 2 different thickets using these 2, the from Caliper API down here on the bottom. So we basically, this first set of data is just getting, or this first set of lines is getting the Caliper files that we're interested in. And then we're reading in the files into 2 different thickets. We do have a TQDM implemented as part of this interface. I guess it didn't render in the Jupyter notebook. We have it off or false by default. Sometimes if you're reading in a really large number of files and you're not sure if it froze or is hanging on you, you might put the TQDM equal to true so that you can see the progress bar of it reading in the number of files. Because this is in Python, you have access to the help method, so you can see information for a given object in Thicket. So if you forget which parameters or what the API looks like, you can call help on the API itself to get the doc string. Okay, so in section 4, looking at the different Thicket components, the first object is the performance data. And so we can view the performance data table by calling, this nice display HTML, or simply you could just call a print on the data frame if you like. That's also equivalent. Which is the HTML rendering shows it makes it a little bit easier to read in the Jupyter Notebook interface. And so you can see, we've got, as some of the screenshots have been showing, we've got a different row for each node in the graph, and then we've got the different metrics that we collected for each of those profiles. And so depending on how many you collected, this will scroll farther and farther to the right. The next is our graph object. So we can call print on our tree API in order to print the Thicket objects graph. By default, so the tree itself is only going to show data from a single profile. And so by default, it's going to select the first profile in the table. So we're looking at data from this 181 profile. And I think that's printed out in our legend here, right? So we print the index of the data that you're printing out on the tree, and you can always change this if you're interested in looking at a different profile of interest. But it's colored by this red-green. By default, we're printing the average time per rank metric because that's, again, built into Caliper, so it makes it easy enough for us to take advantage of that and be able to program that into our print statement. But you can easily switch this to any of the available metrics that you have in your profile or in your performance data table. Okay, so here's an example of switching out the profile. So now I'm looking at a profile's data starting with 245. So this is, 6.766 for this run, and before it was 1.781. Oh, no. Okay. This would. Okay, hang on. Okay. So looking at the metadata table next, we call a similar display function. And so these are going to be much taller each row, but you get a row per profile, right? So there's the 181, the 245 profile that we just visualized. And if we scroll to the right, you can kind of see the different metrics that we were collecting. So you've got the Caliper version. We've got the libraries, what the launch date was, the user, the command line, the cluster that we collected, and so on and so forth. So some of these are already built in. Some of these we've added, or the application has added itself, like GPU targets, block sizes. That's something that the application added to the metadata specifically for this application. Okay, so if we filter with respect to the metadata, we can filter either using the call path, or we can apply just a direct pandas filter. So in this case, we're applying just the pandas filter itself and just going row by row and saying, is this, does this satisfy the filter or does it not? So in this case, I'm applying a filter of looking for problem sizes that are 1 million only, and then I want to filter my metadata. And so that should shorten up things happening with my rendering. That would shorten up the number of rows in our filtered metadata. And I would scroll up and down. Okay, so I believe this should have one row in the metadata table, but it's not letting me scroll up and down. So something's happening there. Okay, so the other thing that we can do is group by using the metadata values. So let's say you've read in lots of different, you've read in all of your profiles, but you want to do this group by function, kind of like what we did for the marble example, where I only want to create a thicket for MPI rank count of 1, another thicket for an MPI rank count of 72, and then I want to take the average, right, of each of these. So for this example, I'm taking a group by on the launch date and also the problem size, and then we're printing out the now grouped by thickets. So we get a thicket per unique combination of launch date and problem size. So launch date is here shown on the screen, and if I scroll to the right, let's see if the problem size is also here. Yeah. So here's a unique combination of this launch date, 16914, and a problem size of 1 million. Here's another launch date of ending in 819, and the problem size is going to be 2 million. Okay, so in terms of our aggregated statistics table, so that's another component as part of our thicket. The aggregated statistics table is a graph frame itself, right? And remember, the graph frame is a component from Hatchet days, which has a graph and a data frame associated with it. And so this table is really, or the aggregated statistics is really useful for doing order reductions over the thicket performance table. So we can display what the initial aggregated statistics table looks like. It's going to start empty. It's just going to have the same nodes in the aggregated statistics table as in the performance table. And then as you start calling aggregate functions, it will start appending columns to this table. So we can filter again on our aggregate statistics in the same way that we were doing earlier. So in this one, I want a very small number of nodes. So I'm looking at Rajaperf, algorithm, and stream multiply. And so when I filter my aggregated statistics table, which we call a stats frame, and print it out, you can see that only 3 rows exist. So we can start calling statistics on our stats frame or over our performance table. So median, for example, we can call on particular metrics like total time. And then when we print out the stats frame, you can see now that we're starting to add in columns relative to what aggregate statistics we're calling. So there's our total time median. There's our total time mean that we're adding now. And then you can see we've got percentiles that are being added as well. So 25, 50, and 75 have now all extended into our aggregated statistics table. And because it's a Hatchet graph frame, when we visualize the tree, we get a very similar terminal-based output, but you can see it's calling the Hatchet variant just with a different header. But we can print our tree out with the aggregated metric that we have now. Okay, so here's an example of using the call path query language. So if you start with this initial call tree, I can't show it, which is many nodes. We scroll down to this cell 18, which is our example call path query. We're looking for any node followed by a node that matches the term or word algorithm. And so this is what gets us the root node Rajaperf, followed by an algorithm parent and algorithm underscore as any of its children. So this is starting to get, again, I point you to the paper by our student Ian Lumsden for more details on how to write more of these different complex call path query language queries, because you can be very, particular in terms of how you write your queries. And it can be a very powerful tool for being able to filter your call tree to look at a particular region that you're interested in. Okay, so this query is slightly different. Let's see if I can get both on the screen. Okay, so it's algorithm 2. So this one, as you'll see, has one extra rel with a star underneath it. And so you can, if I can get both of these trees on here, this one just forgets, ignores the root of the tree. So our subtree is now rooted at an algorithm node, and we grab all the children underneath it. Okay, so I think the last piece of this is displaying a histogram, which we didn't have examples in the slides of, but this is another visualization that we've built into Thicket to allow you to select a node and a metric value and be able to generate a histogram. So here's the help menu on this display histogram function. This is on the aggregated statistics table. And we can print this as simply as, just looking at a binning structure for the total time, and you can customize it. I think we've implemented some of the big categories in the, I think it's a matplotlib plot. So we've brought in some of the customization parameters from that interface so that you have them similarly in Thicket. And so we can, make changes and things to it as you see fit for different presentations or things. These heat maps can become more complex as you stack in more of the, bring in more of the metrics, more of the nodes, so they can become quite large. So I'm going to scroll over those, and this is showing how we concatenate everything together for the heat map. Oh, okay, I guess that is the bottom. So what did we print out last? Okay, this is not going to let me see cells 31 through 30. Stop. Eh. Having a rendering issue. Okay, so I think cells 31 through 34, if I recall correctly, is showing another example after the heat map, but I can't confirm. But this is reading in a different data set from our Raja Performance Suite. We're doing a group by on our Thicket on the tuning value. Sorry, we're doing a group by on the tuning, which is showing up in the metadata. And then we're concatenating the thickets. And so now the tuning becomes a kind of like a subcategory or a subcolumn of our thicket. And so block 1024 has all of these various metrics. If I keep scrolling to the right, there's a block 128. And so again, this is another way for us to be able to get all of the information into a single performance landscape, because block 128, block 1024 were all different runs that we did, but we are able to get all of that source of data into a single place so that we can start to make figures and do analysis with all that information in one place. But the other way that we've done this in the past is that instead of block 512, we might have this as CPU and GPU, for example. We might have this as different rank counts, different node counts, but it's kind of a way for us to categorize the different metrics relative to the runs that they're associated with. Okay, so with that, any questions that I can answer? Great, thank you for people in the chat contributing with the links and things. Yes, horizontal scrolling in Jupyter Notebook can be tricky. Yeah, and so really the HTML view has been the best method for us to be able to go left and right if you do have a lot of columns. But also just printing, doing a call to just print out the columns themselves, so you kind of get a sense of what columns are there, and then you might want to filter your view of the data frame so you don't have to scroll so much left and right. That can also be helpful. Okay. So I think with that, let me see if I had anything else for this one. I think that's all I had to share for the Thicket side. We left some time for Q&A and for wrap up and things. Let's see. NVIDIA has Insight and Intel has Advisor. Do Caliper and Thicket depend on hardware? So Caliper, when you do build Caliper, it is hardware particular, and you also can customize it to turn on, PAPI, support for MPI, GPUs. And so your Caliper install should really be specific to the machine that you're running on and what you want to be collecting. Thicket is all based in Python, and so Thicket's more independent on where you're running it. We have more success running it on x86 systems as opposed to like when we had our Power 9 systems. But if Python is supported on your particular hardware, then Thicket will run as well.
To add to that, like the base functionality of Caliper is hardware independent, so you get your time profile on really anything. It's just for some of the special functionality like collecting GPU metrics where it becomes more hardware dependent and you have to build it for your specific system. But the base functionality is really basically works anywhere.